Okay, so today we're going to do case 7 from chapter 9. It's a proportions problem, an upper tail test involving a proportion. So we go to my teaching page, chapter 9, case 7. We're going to open that up, and we see here that we have a variable, response variable, no's and yeses. It looks like our sample is of size, I think 400. Yep, 400. So our sample size is 400. We're going to use this data to answer the question on the spreadsheet. And it looks like we have a study that in 2005, 12.5% of the U.S. workers belong to unions. Suppose a sample of 400 U.S. workers, which we have simulated here, is collected in 2006 to determine whether union efforts to organize have increased union membership. In part A, the first thing we have to do is formulate the hypotheses. In part A, we want to formulate the hypotheses. So if we go back to the original problem, I'm going to go ahead and make that blue and bold, that number, because that's going to be our hypothesized value. And then we want to know if a year later union efforts have increased that number. So we're going to make union membership, we're going to make that red and bold, and then increased, we're just going to make that bold. Those bold phrases, red, black, and blue, represent the alternative hypothesis. Union membership is the unknown proportion, population proportion that we cannot know. And the 0.125 is what it was the previous year. So in words, the alternative hypothesis says that the proportion of union members increased above what it was last year, which was 12.5%. The null hypothesis is the opposite of the alternative. So I'm going to copy and then just change a couple things. So this is the null hypothesis. If the proportion of union membership increased from what it was a previous year, then the opposite of that is the same or fell. So now the null hypothesis says the proportion of union members in the labor force is less than it was a year before or the same as it was a year before, while the alternative hypothesis says the proportion of union members increased from what it was the year before. Now I'm going to write both these in an alternative form. I'm going to copy and paste them over here, and I can actually rewrite this as P minus 0.25 less than or equal to 0. And I'm going to change that back to black. I can rewrite this as P minus 0.25 greater than 0, and I may change that to black. Oh, I forgot to include equal on this reformulated null hypothesis. So let me underline that, less than. So we have two versions of the null and alternative hypotheses. In part B, we want to compute the test statistic. Now I'm going to go back to my website and download the PowerPoint for chapter 9. In the PowerPoint, remember that sigma squared for a proportions problem in chapter 9 is the hypothesized proportion times 1 minus the hypothesized proportion. And in this case, the hypothesized proportion is 0.125. So we need to determine sigma squared, and we're going to take the hypothesized proportion, we're going to multiply that by 1 minus the hypothesized proportion. And we get 0.09375. That is our sigma squared, or population variance. Now that the PowerPoint is open, we click on it, or downloaded, and then we'll fast forward to a point in this PowerPoint. So here we have the z-stat for a one proportion test. We have p-bar, which is the sample proportion, minus p0, which is the hypothesized proportion, divided by the standard error. This statistic is normally distributed as long as the sample size times our hypothesized proportion is greater than or equal to 5, and the sample size times 1 minus p0 is greater than or equal to 5. Now, in the context of our problem, this right here would be what we expect the number of union workers to be in our sample. 400 times 0.125 is much larger than 5. And if that's the case, then the number of people in the sample who are not unionized is going to be much larger than 5 as well. Okay, so I'm going to go ahead and copy the z-stat here, use my snipping tool, and just cut, copy, and paste it into my Excel spreadsheet. I need to calculate the z-stat, or the test statistic, for the sigma known case in a one mean proportions test. The first thing I need is sigma squared, which I've already calculated. I need the p-bar. So p-bar is a sample proportion, and the sample proportion is the number of yeses. And the way we get the number of yeses is to do a count if. So we're going to go over here, and we're going to highlight all 400 observations. We're going to highlight all 400 observations. So we're counting this blue box if the response is yes. Okay, so we're counting the number of yeses in this blue box with the equal count if function that's available in Excel. Now, every time I hit F9, the number of yeses changes, right? What's going on? Well, we are simulating this study, this 2006 study. So every time I hit F9, I'm essentially saying, hey, I just interviewed 400 different people. Maybe I interview 400 people one week, then I interview 400 people the next week. So what we want to do is we want to freeze our sample. So I want to copy and then paste special, and then double check, and when I hit F9 now, the sample's frozen. Now every one of us in this class are going to have a different P, or number of yeses. Some of us might have 30, some of us might have 40, yada yada yada. So this is not yet P bar, this is just the number of yeses. So what we have to do now is divide by the sample size, which is 400. But I'm going to put N in this cell. So I'm going to have N equal to 400 right there. So my p-bar in my sample is 0.075. We're going to have, like I said earlier, we're going to have probably 25 different p-bars in this class. The numerator of the z-stat is the difference between p-bar and p0. And it happens to be the point estimate of this difference here. P-bar is the point estimate of P, and P-bar minus P0, in this case 0.125, is the point estimate of this difference. So the next thing we have to calculate is the point estimate of the difference. And here we just type equal my P-bar minus the hypothesized value. And there is going to be a difference. As we learned from one mean hypothesis testing, there is a difference between the population mean and the hypothesized value. Just like that, we're gonna have a difference here. But where our interest is the difference significant? And because we have the alternative hypothesis indicating there's an upper tail test, then not only do we want a significant difference, we want a positive significant difference. So we have the numerator of the z statistic. Next, we have to get the standard error of the z-statistic. The point estimate of the difference is the numerator of the z-statistic. The standard error is the denominator of the z-statistic. So we need the standard error, and it is just the square root of the sigma squared divided by n, 400. So the t, or the z-stat, is equal to the point estimate of the difference, the numerator of z-stat, divided by the denominator of z-stat, the standard error. And it is equal to negative 3.02372. Now I'm going to pull this down here to give us a little bit more room. In part C, we're given the significance level alpha equal 0.10, and we're asked to make a conclusion. So with significance equal to 0.10, change the font of that so we have an alpha symbol. The alpha is 0.1. Going back to the alternative hypothesis, we have an upper-tailed test, which means we divide alpha by 1, and I like to explicitly do that to remind me that we do have a one-tailed test. Alpha divided by 1 is 0.1, and if you recall, the sample size is 400, and earlier in the class we mentioned that we can get the z-value, the z-critical value, from the standard normal table, or we can get it from the infinity row of the t-table, because as the sample size gets bigger and bigger and bigger, the degrees of freedom gets larger, and as degrees of freedom go to infinity, the t values become z values. We can find the z critical value in row, or in column 0.1, and the infinity row of the t-table. So let's open up the tables here. Waiting for it to load here. The first one's standard normal, and we want to find 0.10 in standard normal, right? 0.10, the number closest to 0.10 looks like 0.1003, and that is in row, let me blow it up a little bit. 0.103 is in row negative 1.2 and column 0.08. So 1.28 is a good candidate, right? Now let's go to the infinity row of the t-table. We're in column 0.1, and we go all the way to the infinity row, and as we go to the infinity row, notice what's happened to the t-values. They're getting closer and closer and closer to 1.28. So if we use the t-table, we get a critical value that is accurate at 3 decimal places. If we use a standard normal table, we only get one that's accurate at 2 decimal places. So we're going to copy 1.282 and paste it into our Excel spreadsheet. Notice the z-stat is negative 3, and that is much less than 1.282. Our evidence in the sample supports the null hypothesis because the z-value, the z-stat, is less than the z-critical value. Thus, we cannot reject the null hypothesis. Suppose we can reject the null hypothesis. Well, reject the null hypothesis is stating or concluding that the alternative hypothesis is true. The alternative hypothesis is true. If that's the case, then union membership is more than it was a year ago, which is 0.125 or 12.5%. However, we concluded that we cannot reject the null hypothesis at 10% level. Thus, when that happens, we preface the alternative hypothesis, an affirmative statement of the alternative hypothesis, with the phrase, we cannot say union membership is higher than it was a year ago. And that concludes case 7 of chapter 9.